Good afternoon, everybody. I am Tarun Souradeep. I serve as the spokesperson of LIGO-India. I'm currently at IISA Pune and also still associated with IUCA Pune. So it's a great pleasure to talk to all of you today on the quest for cosmic origin. Before I go on to my talk, let me begin by commending the LIGO-India EPO, Education and Public Outreach team, for coming up with this wonderful initiative and executing it flawlessly till now. And there would be many talks ahead. And in particular, again on Wednesday, we will have Professor Bala Iyer, who was one of the lead proposers with us on the LIGO India project, speaking to you about gravitational waves or some aspect of gravitational waves. Please watch out for the. So let me sort of set out the tone. So you've been hearing a lot about the LIGO India project and similar LIGO detectors. What you see on the slide is the picture of the LIGO India facility that would be expected to be up in the middle of the next in of this decade. So about 2025 or even before that, certainly well before that, you will see the buildings and this 4 kilometer length armed laser interferometer in this lovely campus in Maharashtra, the Hingoli district. So let me move on to the topic that I'm going to talk about, which is going beyond LIGO India and what are the challenging projects ahead for folks in India to join into. So gravitational waves can open up in 4 windows, just like electromagnetic waves are seen in radio, optical, infrared, and then UV, X-ray, gamma rays. Similarly, for the gravitational waves, what we have are gravitational waves in the window of milliseconds, which is being probed by the LIGO detectors, LIGO-like detectors all over the world, and including LIGO India, at about 100 times to 1,000 times the wavelength or frequency, longer wavelengths, you will see a gravitational wave from a different class of objects, which you can see from space, laser interferometric space antenna, which is already a project which has been approved as a space project in the in 2030s, early 2030s. And then there are nano second, so I mean not nanoseconds, sorry, nanohertz, so which is longer wavelengths, sources that can be spotted through radio antenna dishes, just like our GMRT spread over the world, particularly the square kilometer array. The window has opened in the milliseconds in 2016 with the discovery of the coalescing or merger of two black holes by LIGO, and there have been many events since then. I will be talking about the longest wavelengths, and I'll be talking about cosmological gravitational waves that have time periods of billions of years, almost cosmic time scales. So you don't really see them as waves, you see them as a frozen snapshot on what is called the cosmic microwave background in the sort of millimeter wave astronomy. And that's again an area of great interest and something as spectacular or even more that is being awaited. So if you had listened to the Nobel talks by the key two of the three Nobel laureates, both mention the discovery of these primordial gravitational waves right from the origin of the universe as the next big science breakthrough that is expected. And why that is that so enigmatic? That's because these would be detecting gravitational waves of quantum origin. Note that the LIGO detection, the gravitational waves that we detected were of classical origin. They were, due to masses moving, macroscopic masses moving there. But these ones would be of origin in the early universe due to ultra high energy physics and very enigmatic, uh, you know, look back into the very, very beginning of the universe. So let me tell you a bit of cosmology to tell you how far we have progressed and how this is only the kind of final frontier of cosmology in a certain sense. So cosmology has been a subject of great interest for everyone for many, many years. I think ever since the first human beings had time to look up at the sky and not worry about being eaten by predators, settled down and civilizations came up, they must have wondered what is our place in the universe. And they would have seen skies as beautiful as this. I'm sure in many cities now, with the pollution clearing out, if again there is a night light out for 9 minutes, you should please try to look up at the sky, and you may end up being able to detect a beautiful Milky Way, which are stars in our own galaxy. But if you look away from the plane of the Milky Way in a dark spot of the sky, what appears dark in the sky, through the largest telescopes, you'll see the Milky Way is just one of many, many, many galaxies. In fact, our universe is made up of galaxies all the way that we can peer in the optical wavelengths. This picture that I'm showing you, which just came up there, is from the Hubble Deep Field. And this field has tens of thousands of galaxies. And some of these splotches are, in fact, galaxies which are so far away from us that the time that it has taken is almost the age of the galaxy itself. I mean, we are seeing the galaxies just forming at that time. So, this is the kind of cosmology I'll be talking about. So, this is the basic unit is a galaxy itself, which is a large object, and it has about 100 billion stars. Each star is about 10 to our 30 kilograms, so 10 followed by 30 zeros. And their light takes about 100,000 years to cross the galaxy from one end of the galaxy to the other. So these are huge objects, but on the cosmological scale, these are just like point speck particles, like dust in a room whose airflow we want to study. We don't care about the structure of the dust when we are doing cosmology of this kind, and we are looking at how the universe evolves, and these galaxies act as tracer particles to that. So let's look at the distribution of matter around us. So in this picture where you see a lot of cloudy structure, we are at the center, and what is plotted around that point is the distribution of luminous matter, distribution of galaxies in the universe. And these clouds are nothing but dense collection of galaxies um, forming clusters and superclusters around you. And this thing goes on into this structure. So if we were to take a flyby through the universe, this is how the distribution of galaxies looks as we kind of come in home from large distances. So there's a beautiful, spectacular filamentary or cosmic, what is called the cosmic web-like structure along which galaxies are uh, present and distributed. And we try to understand this universe that we kind of are observing through the simplest model that we can come up with. And what is the simplicity in this distribution? So you see the distribution of galaxies. If you were not to worry about their position distance away from us and just looked at the projection of galaxies all around us, we see that fairly to a large good approximation. The galaxies are fairly uniformly distributed all around the sky, which gives us confidence that at the kind of very, very basic level, we can assume that the distribution of matter in the universe is isotropic around us. Isotropy means it's the same in all directions. And if we assume also further that we are not in a special location of the universe, that isotropy should be present or should be observed by any observer, any place in the universe, which leads to a homogeneous distribution of matter. It's a mathematical fact which leads to our basic cosmological models. And if you use the laws of gravitation, which is Einstein's general relativity, applied to uniform distribution of matter, that brings about one of the biggest surprises that human uh, science endeavor has ever come up with. If you put Einstein's equation, if you solve for Einstein's equation with a uniform distribution of matter, you find that space expands with time. So it leads to an expanding universe. It's very difficult to create a situation where the uniform distribution of matter does not cause the space to expand smoothly. And if it's uniform, the expansion is the same everywhere, which is what you're seeing in the backdrop to what I've written there. And let me show you that. So it's a nice lattice of regularly spaced galaxies, a toy case. And you can see every galaxy appears to be moving around away from the other. And that's because they are sitting on a space-time fabric that by itself is expanding. So clearly, this was the first time that you realize that space-time was like a fabric. It did have some kind of a stiffness and it can kind of expand due to a particular distribution of matter, uniform distribution of matter. And it's not difficult to imagine then, once you have thought that the space-time is dynamic and responds to matter and has a smooth expansion, it's not difficult to then imagine that if you had a ripple in it, the ripple would also travel like the gravitational waves. And this has been covered very well by Professor Sanjit Mitra in his first talk. And I think this is one way to realize in cosmology itself that space-time does respond to matter, and it's a the expansion of the universe is your first clue that space-time can be perturbed. So there are interesting things that happen in an expanding universe, and one of the surprises is that uh, how the density of radiation in the universe evolves with time. So I told you that we are in an expanding universe. So let's draw an imaginary box around a number of galaxies, which you see here. And the box is expanding with time. So the number of galaxies is the same at every time in that box, including the box includes the same number of galaxies, but the size of the box has grown by a factor of 2 and then another factor of 2 in the next step in my picture here. And the number density falls off as a factor of 64 by the time you get here. Similarly, the number of photons, if there was instead of galaxies a bunch of photons here, that would also go down in the same way. But in addition, photons are different from a galaxy. Photons, the wavelength also stretches with the expansion of the universe. So not only do the number of photons fall off with the expansion of the universe, the photons wavelength also scales up by a factor of 2 and then 4. And hence, as you know, the energy of light is given by its frequency. So if the wavelength stretches, the frequency goes down, and consequently, the energy of the photon goes down. So what you'd find is that the energy density of radiation falls off faster than the energy density of galaxies. At this point in the universe, if you were to take all the mass in the observed galaxies and divide by the volume, then the density of energy, where you take the mass and multiply it by c square and make it an energy density, uh, is about 10,000 times more than the energy density of radiation. However, what is interesting is since radiation density has been falling off faster than the matter density or the density of galaxies, in the early universe, when the universe was a factor of 10,000 smaller, the energy density in galaxies was the same as radiation. And in an universe earlier than that, the energy density was completely dominated by radiation. Okay, so the early universe is radiation dominated, and hence for 25 years, people were hunting for where all the cosmic radiation was. And this was discovered serendipitously in 1965. This itself is a great story, and I'm sure many of you have heard about it. Of the first radio antenna being tested, one of the early radio antenna being tested in 1965, and it had a noise that wouldn't go away. And finally, people concluded that what they had discovered was this cosmic radiation that is actually accounting for 99% of the radiation content of the universe. It is distributed extremely isotropically, so up to 10 parts in a million, which again lends much more support to this idea of a isotropic and homogeneous universe that we have. It's a black body in some sense. Any object which is heated, and a good black body emits a spectrum which only depends on its temperature, and we can determine the temperature of the radiation very accurately now. We have determined it to be somewhere around 2.7 degrees above absolute zero. And this tells you that the universe must have expanded from a state when it was about a factor of 10 million times smaller. This observation itself, that it's a black body, tells you that. And then you can take that further and say that the universe going further back in time was even denser, even hotter. So, where is this radiation coming from? So, the radiation comes to us from an amazing natural setting. So, if we are here and now at the center of the picture, as you go out and look at a distant galaxy, you are looking back in time, realize that time, like you're seeing the galaxy as it was in the past. You go further up, it's a galaxy which is even back in the future, in the past, and then you keep going back till you hit a universe, a point in the when the universe was only 500,000 years old. Note that the universe now is about 14 billion years old. And at that time, the universe was at hot by a factor of 1,000. The radiation here is 3 Kelvin. Radiation there was 3,000 Kelvin. And everything atomic, like hydrogen and helium, was in a plasma state. So what we have, naturally set for us is a plasma screen all around us. It encloses us in all directions around an observer here, which is emitting radiation at about 3000 Kelvin. But by the time the radiation comes from that surface all the way to us, it has redshifted to a temperature, or it has become cold, 3 Kelvin bath. But it carries with it all the information about a universe which was 500,000 years old, all the way to a universe which was 14 billion years old. And it's in fact the furthest, this 43 billion light years is almost the furthest that you can look out in terms of electromagnetic radiation. Beyond that, you hit a opaque surface, a plasma screen does not let you see beyond it. And so it's amazing plasma theater where we have started exploring the early universe. And this is called the cosmic microwave background. And going further, you could also realize that in the orange patch where my pointer is not showing too well, information can come beyond it from things that do not couple that strongly to matter, like the electromagnetic thing. Such things would be neutrinos, and even further weakly coupled are gravitational waves. So this is the cosmic theater in which we will study, and we have these galaxies there, the distribution of galaxies. And as you notice, that the distribution of galaxies, as I pointed out, is fairly the same everywhere, but not exactly homogeneous. If you look in detail, you see that the galaxies are distributed on this very filamentary structure. And that sort of reflects in the distribution of radiation. And 25 years after the discovery of the microwave background in 1992, another satellite called the Cosmic Background Explorer started looking at the microwave background with the sensitivity of 10 parts per million to be able to discern that the temperature was slightly different in different direction in the sky. So you could at least see not a blank screen at about 2.7 Kelvin, but you saw a screen that was perturbed. And that has all the implications for what I'll be talking about now. So that tells you that the screen was already perturbed when it was 500,000 years old. So there must have been some phenomena in the early universe which had perturbed it. So that I've schematically shown by the origin of structure. So things that have perturbed this plasma screen. And the mechanism that we have to perturb it also generates for you necessarily a gravitational wave background. And both these density waves and the gravitational wave background actually cause these fluctuations in the microwave background that we can study. But what we have studied till now is the resultant of these fluctuations. You have these fluctuations in a universe at 10 parts per million when the universe was 500,000 years old. And you have seen that those fluctuations have grown to give you this distribution of galaxies in the current universe, which is about 14 billion years old. And we understand this part of this diagram very well. We understand how to connect this mildly perturbed universe to the universe, which is, we see in here with a rich distribution of galaxies, clusters, and superclusters. So what's happening on this plasma surface? What's happening is essentially something like what happens on a drum. Remember, space-time is like a fabric, and on that you have this plasma distribution. If the fabric is perturbed, it perturbs the density of the plasma, and plasma behaves like elastic medium. It's more or less like getting waves on the surface of water. So if you have a lake and there's a burst of shower, everywhere there'll be ripples created. Similarly, if I were to create a droplet on the surface of the plasma screen, there will be a ripple created that will run out in a wave that will travel a particular distance of 150 megaparsec before it stops, because the universe sort of the atom and the radiation stops being gets decoupled from each other when the temperature falls below 3000 Kelvin. So when we are out of the fog area, that's when so what you are seeing imprinted on the plasma screens is a random superposition of such spikes with a ring around it. And that leads to fluctuations in the microwave background, which can be studied in the Fourier domain. And so that is to identify this particular length scale of 150 megaparsec that you see in the sky. So if you were to look at the distribution of the temperature in terms of angular scales, you would see that for a given universe, that curve This depends sensitively on the amount of normal matter we have, the total density of the universe, the expansion rate of the universe, and various other cosmological parameters. And we understand the variation very, very well through very basic physics. And it is essentially a series of harmonic peaks. I told you happening in terms of rings around spikes translates to a harmonic series of peaks in the Fourier domain, in the domain where we are looking at inverse angular scales. And you can pick up this scale of 150 megaparsec, which is related to the location of the first peak and the height of the first peak. In fact, you can imagine that since only ordinary matter couples to radiation, the more ordinary matter we have in the universe, the higher will be the peak of these fluctuations in the microwave background. So much so that uh, if you had about 4% of the matter in the universe to be made up of ordinary baryonic matter, baryons are just normal matter that we have seen in the lab, then the temperature ought to be at 74 microkelvins. Further, another information that is available to us from this picture is the geometry of the universe. We are seeing a length scale of 150 megaparsec placed about 43 billion light years away. By the way, I didn't say what a parsec was. A parsec is about 3 light years. It's something. So essentially, the stick is about 450 million light years in length here, placed at a distance of 43 billion light years. Even a child can sit and calculate the angle that it would subtend to us if the universe is geometrically flat, as we have learned uh, in normal geometry in our schools. The angles would add up to 180 degrees. In case the universe was not, if it was geometrically a surface of like a surface of a sphere, then the angles would add up to more than 180, in which case this angle would be bigger than this one shown in yellow. Or if it was what is called a negatively curved universe, then it would be smaller. And if it is exactly flat, as Euclid had told us, and the geometry that we learned in our school days, then the location of this peak should be at an inverse angular scale of about 220. So this was all known, and we set off from 1990s. That's around the time I started my research career with results from the Cosmic Background Explorer, which was the first decade of results. Then in the next decade, when by the time I'd already become a faculty member, we looked at the next satellite images, which were at much higher resolution and sensitivity, 25 times uh, probably um, better than Kobe. And then we have looked at this current decade, where we have basically in the rather the last decade of 2020s, 2010s, 2011 to 2019, Planck has been making much higher resolution maps of the microwave background. So much so that we have a beautiful picture of the plasma screen now, which I have showing you is real data from the Planck satellite. So we have already got a huge amount of information that we could get from the density fluctuations of the plasma. And if we look at Fourier's domain, then lo and behold, we find that the curve is such that the first peak is exactly at an amplitude of 74 microkelvin, and it is located at an inverse angular scale of 220. And we hence know that the universe is flat, geometrically flat, and it is in fact got only matter that clusters, and matter, the only other thing that can exist in the universe is matter that does not cluster under gravity or vacuum energy. From the distribution of galaxies that we have measured, and how they would evolve from a universe which was perturbed just like the way we see it perturbed in the microwave background when it was 500,000 years old. You can run sophisticated simulations, computer simulations, and ask if all the matter of the universe is, you know, dark matter, or is it got something more surprising, matter that does not cluster. And we discovered that, in fact, we are inhabiting a universe which has a substantial amount of matter that is not only dark but also does not cluster under gravity, and is goes by the name of a cosmological constant or vacuum energy. So at this point, we are in a very interesting stage of cosmology where we've closed the chapter on basic cosmology. We understand that the basic model of cosmology, with few parameters, explains the universe from the beginning to how it would evolve into the past. And amongst the many curves here, we know that we have a particular universe which is shown in red, which is going to expand forever at an ever increasing pace. With the microwave background data, you can determine all of this together, and you can see that these green dots showing you with error bars showing you the measurements of the Planck satellite. And what is shown here is this black line that you would predict if the universe had a different matter content from what we derived. And you can jointly change all that in a sampling of the parameter space and slowly home on to the combination of parameters that lead to a universe which exactly fits the data. And those give rise to amazingly accurate estimations of how much ordinary matter is in the universe, how much of cold dark matter is there in the universe, and various other parameters. All these numbers are amazing, that we are sitting on a tiny speck of dust in the universe, which we call our Earth, and we can tell with confidence the total amount of atomic matter in the universe to a percent accuracy. We can talk about the expansion rate of the universe to a little more than a fraction of a percent accuracy. And that is the standard cosmological model. So we know that basically we understand the model of cosmology extremely well. We understand our universe extremely well. Okay. It is a simple yet exotic universe. And this understanding is what was celebrated in the Nobel Prize given out last year in 2019. The fact that we are in a universe where 95% of the energy density is in some exotic form, non-atomic form. A large fraction of that is cold dark matter, matter that we cannot see directly, but we can feel it through the gravitational effect. And but even more, there is matter that is dark, smooth, and which actually acts repulsively under gravity. All these are now almost a matter of fact that we are forced to accept in cosmology. But the biggest clue we have got is there is physics to be uncovered at ultra high energy scales. That's because you remember that all the deductions we made about the universe was based on the fluctuations that we saw in this plasma screen. And it begs the question, what created those fluctuations in the first place? There must have been an ultra high energy phenomena in physics that we haven't yet uncovered. We have uncovered very, very amazing things in high energy physics. For example, recently we have learned that all the mass of the particles in the universe is given by the Higgs field, and we have discovered the Higgs particle. Similarly, we expect that there have been scenarios of unified theories of all interactions, which would have scope to create a situation where the universe does create these perturbations. So, who created these perturbations in the universe, or who pinged the cosmic drum? Okay, and that's the question to be asked. And the answer we have is pretty exotic. The answer is that we believe there was a phase of very rapid expansion of the universe where space expanded by 30 orders of magnitude in the space of 10 to a minus 30 seconds, right? So it's an unbelievably fast expansion of the universe. We also understand from our understanding of quantum physics in such an expanding universe that the quantum fluctuations in such a universe will get frozen into the kind of density perturbations that we see in the universe now. And that is the first part of the diagram that you see here. And whatever we have learned from cosmology now, using the data from Planck, is in the second half, where you have these fluctuations generated in the very early universe, which is perturbing the plasma screen placed 43 billion light years away. And given those fluctuations, we understand how the distribution of galaxies evolved. And from connecting this to the picture in the middle to the picture in the end is where we understand how our what is the content of the universe and what is its expansion rate. And we are very confident about those numbers. And that is the time to discover the very beginning of the universe. This inflationary epoch can be almost dubbed as the creation of the hot Big Bang universe. So, as I alluded to in my first picture, so we are looking for the driving mechanism for fluctuations in the early universe. And the unique aspect of that is if inflation or that kind of a high energy physics phenomena was responsible for all the fluctuations or the galaxies and superclusters that we see now, those same quantum fluctuations that gave rise to density perturbation, the same quantum phenomena would give rise to gravitons or a gravitational wave background right from the beginning of the universe. And that is what we are striving to pinpoint in cosmology now. Look at the smoking gun of creation. Okay, and at this point, we have only upper limits on that. But to find this gravitational wave background is kind of a to do or a must do for cosmology, and is actually the next big scientific breakthrough that is expected. Where again, just like we became partners on a breakthrough like the detection of first gravitational waves, we would like to see a huge Indian participation in a breakthrough where we see the universe, the gravitational waves from the early universe. Now, these gravitational waves are kind of interesting. Those, as I said, are very long wavelengths of cosmological scales. So they essentially, you go back to this picture of this plasma surface that is surrounding us. So you can imagine that there is this plasma sphere which is in the universe, and there are long wavelength gravitational waves, almost comparable to the size of the sphere. And what they do is a gravitational wave, if you have learned in your first lecture, just does not squeeze and pull, but it can also shear space. So what it will do is it will shear the round ball that you have into some distorted ball. And a very exaggerated picture of this is a gravitational wave going through from the bottom of the screen to the top, would distort the plasma screen in this fashion. And that leads to very peculiar distribution of the polarization pattern in the microwave background. I did not mention, I only talked about temperature fluctuations in the universe, in the microwave background in the sky. But the microwave background is also linearly polarized with a different direction of linear polarization in in different parts of the sky. So this is the entire sky map with color you see the temperature fluctuations, and in stick, you see the linear polarization pattern. And in this pattern, which we have already detected a part of, there are hidden patterns of a particular kind, which are worlds, which are not radial or tangential, but you can see worldly kind of patterns. And these are telltale signs of gravitational wave background. And these are expected to be at 10 to 100 nanokelvin level. So let me recount. We have a 3 Kelvin bath of cosmic microwave background on which we first detected with COBE uh, fluctuations at the level of tens of microkelvin in the temperature. Subsequent years, we started detecting a pattern of linear polarization, which was a factor of 10 weaker. Now, again, a further factor of 10 weaker would be this pattern of worldly structures, which tells you that we need to go and look at experiments which not only map out the spectrum that I showed you very beautifully uh, mapped out by Planck. We remember the black curve with many, many beautiful points, very tight points around it, which is this red curve. But we would like to measure also the power spectrum of linear polarization, which necessitates a new generation of satellites that will go out to map the cosmic microwave background. And this is again like breaching a boundary. So LIGO breached the boundary of length measurements. So LIGO probably measured the smallest length displacements that you can ever think of measuring. It measured changes in length at the level of 10 to the minus 18 meters, which was unprecedented. Similarly, now we'll have to breach another boundary of our ability to measure power. Now, what is amazing is your cell phone is a very, very good, receiver of power. It can measure picowatts of power. Remember, you typically deal with 10 or 100-watt bulbs here, or micro milliwatt kind of LEDs. But now we are looking at FM reception or cell phone reception at 10 to the minus 12 watts or picowatts. But we have to have better receivers. So the 5G were the kind of receivers that are coming to your phone, were the kind of receivers that were flown to measure the kind of polarization patterns that we have measured now. But we need a new state-of-the-art detectors which can measure atto-watt of power. We need to place them in huge arrays of 2,000 to 10,000 detectors and launch them on a satellite to space. And we have in India an Indian Cosmological consortium called CMB Bharat that has made a proposal to ISRO exactly seeking to do that. So that is going to be a near ultimate CMB polarization survey. We will exhaust all the information available in the cosmic microwave background or on this plasma screen, written on the plasma screen with such a satellite. And amongst many, many great goals, one is to improve the cosmological model or discover neutron physics. The ultimate goal there will be to discover primordial gravitational waves that will reveal the signature of quantum gravity and ultra high energy physics. Okay, so this would be yet another breakthrough that will happen in the lifetimes of many of us. And so the plan is to launch a satellite which would weigh about 2 tons. We will use our maximum launch capacity, which is the GSLV Mark III, on which Chandrayaan 2 was sent, for example. But here we would actually launch far away from the Earth and Moon system into a direction opposite to that of the Sun, to a location called the second Lagrange point. And the satellite will have a loose orbit around that quasi-stable point, look away from the Sun and map the cosmic microwave background at unprecedented sensitivity. So let me stop there with this story of gravitational waves from another window, and now the cosmological window. As I said, cosmology has made great progresses with the CMB satellite that was launched in 2009 by the European Space Agency. And we hope that the next mission would be for India launching the next cosmic microwave background satellite called the CMB Bharat mission, and discover the prized quest for the origin of the universe. Thank you very much. I'll take questions, which will probably be sent to me if there are questions. One of the things about giving a talk on this YouTube channel is okay. So the questions are coming in. So this question is from Siddharth Chatterjee. The universe is expanding, and we are also part of our universe. So do our body and other objects around us expand? No, Siddharth. What expands are things that are not bound by any forces. So there's a concept of something being bounded in an orbit, like Earth is in a bounded orbit, gravitationally bound orbit around the sun. And if it is bound already, then the expansion of the universe does not expand the distance between sun and Earth. Okay, so it's the average distance of empty space that is changing between galaxies. But the galaxy itself is a bound object, gravitational bound object. Now, if you come down to objects such as our own body, we are bound by even stronger forces of electromagnetism, which is like 40 orders of magnitude stronger. And there's no question that the expansion of the universe would be able to expand us or any system that we have which is bound by electromagnetism. Okay, the next question is Krishna Buttada. Again, it's the same question. While the galaxies are moving apart from each other, what is the effect at the atomic level of this expansion? It's minuscule. It's incalculably small. Again, because the electrons around an atom are bound by electromagnetic forces, and they are very strongly attached to the nuclei, which is positively charged. And so the ratio by which the expansion of the universe to this is, about 40 orders of magnitude. So if there is an expansion that is, minuscule and not relevant. The Kamal Arasan has asked, is it possible to identify the center of the universe using the microwave background? Okay, Kamal, there is no center to the universe. The universe is the same everywhere. So if you look at the surface of a smooth ball, then there is no, say, point which is at the center of the surface of the ball. There's a center to the ball itself that is separate. Or if you look at a flat infinite sheet, there is no point which is. So similarly, the universe doesn't have a center. But your question does point me to a question, issue. There is, of course, a cosmic rest frame of the universe. Okay, there is a frame in which the universe and all the particles can be called to be at rest with respect to the expansion of the universe. And that frame can be pinpointed by the cosmic microwave background. In fact, that in two manners, and we know from that, for example, that our own galaxy is moving at about 600 kilometers per second with respect to the microwave background. So we see the microwave background red shifted in the opposite direction and blue shifted in the direction of our motion. And there are other subtle ways of seeing the same effect. Uh, Sakshi Nigvekar asks, how do we measure redshift in gravitational waves? It's Gravitational waves are very much like light waves. So redshift means a change of wavelength. And if we know what the wavelength was at the origin, we can measure, and we measure it at a different wavelength, we can measure the redshift. In fact, gravitational wave uh, sources of, from compact binaries, there is some information which can give you the redshift, because if you look at the pattern of frequency variation that you'd expect in a coalescing binary, if it is at a significant redshift, you will see that same pattern but redshifted. Okay, and this is something that is possible to do. And in future, there will be speakers who do it as a part of their daily work from the data that is coming in from the LIGO detectors. So I would encourage you to attend talks by Professor Bala Iyer, Professor P. Ajit, who would be, uh, telling you exactly how you can detect the redshift of gravitational waves. Rahul Divedi has asked, is gravitational wave longitudinal or transverse type wave, or is it completely different? No, it is very much uh, a transverse wave, just like electromagnetic wave. And so essentially all the action is happening in the plane perpendicular to the propagation of a gravitational wave. And so it's a transverse wave, and there's no longitudinal component in standard Einstein's gravity. But I should also mention that amongst the many things that detectors like LIGO allow you to do is a search for any possibility that there are longitudinal modes of gravitational waves, which will tell you that gravitation is different from Einstein's gravity. And there are so-called different degrees of freedom to gravitational waves. But in Einstein's gravity, which we have no reason to, at this point, to doubt experimentally, consistent with all experiments till now, it is expected to be transverse. Okay, Rutvik Pathak has asked, is the CMB Bharat proposal approved? I wish I could say yes, but that's not the case. It's a very, very expensive proposal, which involves international partners. At this point, it is being studied by ISRO. So there have been, committees set up to understand the technical benefits that India stands to gain from taking up such a project. And we expect that we will slowly make moves towards, a possibility where we also need to rope in partners. When we proposed it, European community had shown interest in joining us, but we will have to have similar understandings developing between the space agencies. Okay, I think we've run out of questions from the audience. Maybe you can quickly tell our team. There is another one. That's an interesting. So Shubhadeep Dey has asked whether the deformation of the LIGO arms are directly by the gravitational wave, or the gravitational wave distorts Earth, which causes the expansion and contraction of the LIGO arms. No, it's a direct coupling of the gravitational wave to the freely suspended mirrors that is being measured. In fact, we take great pains to isolate the laser interferometer from anything happening on the ground. It is true that the Earth also gets squeezed and stretched as gravitational waves go, but that is not what we are measuring. We are measuring actually the coupling of gravitational waves to the mirrors that are at the ends of the interferometer. So I should tell you that we have various ways of contacting the EPO team. There is LIGO-India _outreach at iuca.in, where you can write your queries about any of the talks and any other questions you may have about the LIGO detector and other future gravitational wave observatories. Okay, Parth Bhagwat has asked a question. If dark matter is the one which does not interact with other things, then how does it affect primordial gravitational wave? It does not affect gravitational waves. But dark matter, I should clarify, is dark because it does not have electromagnetic interaction. It does have gravitational interaction. And in fact, it would lens gravitational waves just like ordinary matter would, and through gravity. And it is not that the dark matter, I mean, the way the primordial gravitational wave is being detected, if you understood what I said, there is a plasma screen in the universe, which is basically a sphere, surface of a sphere of 43 billion light years in radius. Okay, so you can imagine a spherical ball of plasma and something kind of perturbing it and squeezing it and stretching it in various ways, and which are the primordial gravitational waves. And they may change the pattern of temperature fluctuations and polarization fluctuations on that surface. They're coming from that surface, and that's what we detect. Okay, Rahul has asked, after a gravitational wave hits an object, does the object's position change completely, or object's position is restored? The object's position is restored because it's a wave. So, it is like tidal. First of all, it is relative movement. So, like a tide, it separates the two objects, brings them back together. So it's a wave. So it will, given the frequency of it, the objects will do something like this, right? So it will move back and forth. So once the gravitational wave has passed, then the objects again get back to their, uh, original position. Okay, Divyanshu Tiwari, do colliding galaxies produce gravitational waves? Yes, they do. And that those are waves. So there would be waves, but galaxy is a rather fluffy object. So those waves are not strong enough for anything to be detected. But however, at the core of galaxies, there is most galaxies or almost all galaxies, there's a supermassive black hole. And when two galaxies collide, what happens is if the cores come close enough, then the supermassive black holes at the center would eventually come close enough and start coalescing into a single black hole. And the signal from that would be measured, but at nanohertz frequency range, which is the place where pulsar timing arrays are sensitive to. Abhijit Chakravarti, can gravitational wave and mass be interconverted like pair production by photons? Yes, in principle, it does happen and should happen, but it's not something that we see happening usually. It would happen at energy scales close to uh, 10 to a 19 GeV, which is giga electron volts, which is kind of the Planck energy scales. Okay. I'm waiting for a signal from the EPO team whether there are more questions. Okay, I'm told that many people would like to know about the quantum origin of gravitational waves. Okay, the quantum origin of gravitational waves brings me to the question that was asked just prior to this: is there pair production of gravitational waves? Yes, and that is essentially what is happening in that during that rapid expansion of the universe. And these gravitational waves that have been produced during inflation are in some sense what is called vacuum polarization. So it is similar effect of creation of virtual pairs of gravitational waves. And that is the reason we call this cosmic gravitational wave background to be of quantum origin. Okay, so I have a couple of questions passed on by the team. Srinjana Raut, please explain why CDM is specifically termed as cold. That's because dark matter is dark, so it can be matter. It's essentially any matter that has very weak coupling to electromagnetism, and but if the matter is light, of light particles like a neutrino, massive neutrino, then it would actually move relativistically up to a up to a long time in the expansion of the universe, in the history of the universe. And these are called hot particles because their way of generating structures in the universe is different from dark matter particles, which are heavy and hence moving non-relativistically during structure formation. So this is a difference. So during the epoch of structure formation, early structure formation in some particular manner of speaking, when structures were being formed at the in response to the microwave background fluctuations initially, hot and cold dark matter would behave differently there, and we can distinguish between them, and we know that the dark matter is in fact was non-relativistic at that time. I think there's also a question, can you elaborate what is that plasma screen essentially? Okay, so for that I probably need to go back to this picture. The plasma screen is something that is around every observer in the universe. Okay, and what is happening here is I'm trying to let me end the show and try to see if I can find a picture that I had actually hidden. Okay. So let's go between these two pictures. So this is the plasma screen that I was talking about. And this orange band that you see is essentially a cut through a two-dimensional version of a three-dimensional sphere. Okay. And what is this plasma surface? So to understand that, we'll have to look at a space-time diagram. So here is the universe at these orange flat surfaces evolving in time. These are this is an universe which is we are here and now. You can see that light or anything that we see in the universe comes to us along what is called a light cone. Okay, so a distant galaxy will be somewhere here, here, here. And then as I'm moving down the light cone, you can see that I'm going back in my time axis. So I'm going to a hotter universe. I move down further, and then I hit a time when the universe was about 1100 times smaller expansion in expansion factor than now, relative to now. And the universe is at a temperature of 3000 Kelvin everywhere. But we can only see this ring in that universe. So this is a two-dimensional universe evolving in time. Now, if I were to take a three-dimensional universe evolving in time, then this ring will be essentially the sky all around us. Note that the observer, which is always sitting at the center of this picture at every time, the ring intersects every line of sight away from the observer. So the observer sees this ring somewhere here somewhere here along any direction along its light ground. And that is the plasma surface where we are talking about. Plasma screen, because the universe is hot enough for the universe to be a plasma state prior to the time when it was 1100 times smaller than it is now. Mitanshu Thakore has asked, can gravitational waves convey any information about dark energy? Yes, they do. If you have followed some story of the 2003 Nobel Prize, which was given to the discovery of dark energy from supernovae, measuring high redshift supernovae, gravitational wave sources from distant universe can act as standard candles and allow you to do a similar kind of a deduction. And that is a very promising line to attack dark energy. Okay, now Srinjana Raut has asked again, you mentioned that several unclustered dark matter has been proposed to exist. We know that dark matter has a property of clustering. Can you explain? No, I'm sorry if I've not been clear. There is dark stuff that is, when we call dark matter, we typically refer to clustering matter. So I'm sorry if I had when we talked about something, the energy density that is dark but not clustering under gravity, it is what is called dark energy. Yeah, sorry if I have not been clear about this. Okay, now Amar has asked, can you give us some career advice, how to go for a career in astronomy from different backgrounds, like engineering, basic sciences, etc.? Okay, so here I come very helpful. I come from an engineering background, so I did an undergraduate in engineering. Most astronomers or astrophysicists and physicists come from physics background. They would have done a master's in physics typically. So I should explain to you what astronomy means. Astronomy is a branch of physics. Astronomy and astrophysics is a kind of physics. So what you need to do is to build up a strong base in basic physics. And there are many institutes like IUCA or ICES or everywhere where we take students with engineering background too. And of course, the other route is more straightforward, which is doing a Master's of Science. Many engineering students who want to move to physics may also benefit from doing a master's after their BTech. You, of course, add an extra year of study to your career, but I think that's often very helpful. I've seen a lot of people being very successful. I should also say I have had students, many students in my career, and they have come from all the different possible streams: engineering, physics, engineering to master's of physics, and then PhD, or directly from engineering to a PhD in physics. It's all possible. All you have to do is build up a fairly good base in physics by the time you finish your undergraduate. I hope that answers the question. Okay, how can we get presentations and study material like this? This will be uploaded somewhere. Yes, it will be uploaded at the LIGO-India web page, and it will be available also on the IUCA SciPop YouTube channel. I think it's definitely available on the YouTube. Presentations like this are there in many such places. I encourage you to write to ligoindia_outreach@iuca.in for more information. I think we are done with all the questions now. It's been a pleasure talking to you all, and I am just waiting for a go ahead from my team to say that we can call it a close. Who would be looking at this video posted later. And it's been a pleasure talking to you. And please do feel free to write to me or the outreach team if you have more questions. Bye.